Okay, back to the worksheet problem where we had a car slowing from 20 meters per second to the left, or in the plus x direction in this particular case, to rest in 8 seconds. And we're going to call the direction that the wheels are rotating the positive rotation direction. What's the angular velocity of one of the wheels at time t equals 0? Given that the wheels are rotating in the positive direction, it should be a positive answer. And to get this, we need, at time t equals 0, all we know is that it's moving at 20 meters per second in the plus x direction. So we can use that relationship we obtained just before stopping the last video. V axle equals r omega. The speed at which the axle is traveling relative to the ground is the same as the speed of the car. So V axle is 20 meters per second, and we know r, so we can figure out what omega is. And here we only really care about the magnitude of omega, but the angular velocity in this case is positive. So the omega we should be getting is 20 meters per second divided by 0.3 meters, which is 66.67 radians per second. B, what's the total number of revolutions each wheel goes through before stopping? So each wheel is rotating, it rotates slower and slower and eventually comes to rest. What is the total change in angle expressed in revolutions it goes through before stopping? And that sounds like a constant kinematics kind of problem. In this case, we know the car is changing its velocity at a constant acceleration, and since its velocity is changing at a constant rate, and that means from this relationship, omega is changing at a constant rate, and that means we're in a situation of constant alpha if we just focus on the rotation of the wheels about the axle. So we can use our constant alpha kinematics equations, and here is the one we know it's 8 seconds before stopping, so we know the time, and we want to know the angle that it goes through, so I'm going to use the one that relates angle to time. And in this case, we already know the initial angular velocity, if we call t equals 0 when it's going at 20 meters per second, is the answer to the final problem. Our alpha we can get from the definition of alpha. If alpha is constant, the average alpha is equal to the instantaneous alpha, and average alpha is delta omega over delta t. Omega final is 0, and omega initial is 66.7. So omega final minus omega initial is minus 66.67, and delta t is 8 seconds. That's how long it takes to make that change. So that's our alpha in this coordinate system where counterclockwise is positive. And so I've got my alpha, I've got my t, I've got my omega 0, and so I can calculate what theta minus theta 0 is, the total change in angle, by plugging all those things in. I get 266.69 radians. We were asked for the number of revolutions, so I know I have to do a quick unit change, which is that multiply by 1 here. There's in 1 revolution, that's the same thing as 2 pi radians, and I've done that to cancel out the radians. So I get 42.4 revolutions about. All right, let's move on to a different topic now, which is the notion of torque. And so here we're just starting out with a voting question to gauge your intuition about torque. You actually have a lot of intuition, and you use things in the right way that take advantage of torque because you have a lot of experience with trying to rotate things. Which of the 6 forces pictured? So we're going to be able to push in any of the 6 arrow directions we can with the same magnitude force would be most effective in getting a tightly stuck nut to rotate. So you got a nut on a bolt that is rusted shut, and you've got this huge wrench. Which way and at which location would be the best, give you the best chance of getting it unstuck, getting the nut moving? This is supposed to gauge your intuition, so we don't really have a proof of this yet, but it's going to motivate a definition. The answer is we know pushing close into the nut is going to be very ineffective at getting the nut moving. We always push as far out as possible. It's similar to if you've got a door that's very heavy and you want to open the door, and let's suppose you've got a door that's really hard to push, and you want to open it by pushing it outward, and it's pivoted on the usual door axis. you don't push right next to where the hinge is. That would make it really hard to open the door. Instead, you push as far away from the hinge as possible, so as far from the rotation point as possible. And you also don't push parallel to the direction of the door, or even almost parallel to that direction of the door. You push in the direction perpendicular to the door. So here, we'd be most effective at pushing with that equal force in the direction perpendicular to the direction that is defined by the direction from the rotation axis to the point at which we're applying the force. So E, it's just testing your intuition. Hope most people have that intuition, that would be the most effective. So this helps us give the definition of torque. So loosely speaking, torque is a measure of the effectiveness of an applied force at starting rotation about a certain axis. Or if something doesn't have resistance to rotation, it might be at starting it angularly accelerating around that axis. How easy is it to get it to start rotating? It's something that's analogous to force. Force tells us the effectiveness of pushing at getting something accelerating or moving along a linear direction, whereas torque tells us the effectiveness of getting it rotating about an axis. Okay, that's an intuitive definition. Now let's go on to the mathematical definition that really defines what it is. So here we've got, I'm imagining this strange shaped object, which is a rigid object, and it's pivoted to rotate around a fixed axis, which is right here. So we can imagine an axis coming out of the screen right there, and it's going to start rotating. So this bump would rotate around this in this direction. So let's suppose that thing's just sitting there, and all of a sudden I reach in and pull with a string that's attached to this point right here. So it's attached to the dot, and I pull with a string, force F in that direction. What is the torque that we're applying to this? We're going to give a definition that's consistent with that intuitive idea we explored in the last voting question. Well, we're going to define the displacement or vector that separates the axis of rotation from the point at which we're applying the force F. We'll define that to be the vector R. And then what we found out in the previous slide is that our intuition tells us that pushing along this radial direction isn't going to be effective at rotating this thing at all about the axis. If F were directed along this direction, we wouldn't succeed in rotating at all. And so it's only the perpendicular component of the force which is important for getting it rotating. In other words, if we decompose F into its radial and tangential component, it's only that tangential component which comes into the effectiveness at rotating it. So I'm going to continue this vector on. If I extend R outward there, if we'll label the perpendicular component of F, or we could call it tangential, but usually I call it perpendicular. Perpendicular to what? Perpendicular to that R direction. So the component of F which is perpendicular to the R direction we'll label as F perpendicular. And the torque is going to be defined by R times F perpendicular. The length of this vector, how far away from the rotation axis you're applying the force, times that perpendicular one. In other words, the farther farther away from the rotation axis I push, the bigger the torque. The bigger my perpendicular component of force, the bigger the torque. That agrees with our intuition on the wrench problem. Okay, so that's one way to do it. And there's a sign convention for torque, but we don't know the sign unless we define what the positive direction of rotation is. So if I say this is the positive, in other words, this is what I'm going to call, if it's rotating around this direction, I'll call that positive omega, or in other words, theta is increasing around in this direction. That's what I mean by the plus sign there with the little curved arrow. Then the sign of torque we're going to define to be a positive torque is one that tries to push it in the increasing theta direction. So for example, in the situation here, we all know if I push in this direction, it's going to succeed to some degree in starting to get it to rotate around in that direction. So it will try to get it to rotate in the increasing theta direction. So that would be a positive torque. Whereas if I pulled with a force in this direction, it would, or if I pull with a force in this direction, down there, it's going to try to rotate it in the negative angle direction. So we would call that a negative torque. You've got to define what the direction of positive rotations is to know what the sign of torque is. So we'll be careful to do that in every problem. Now, there's a different way to write this, which is sometimes more useful. In fact, there are two more ways to write it. If we go along the r vector direction and keep going, then we say, how much do I have to deviate from that direction? By what angle do I have to deviate to reach my force direction? So relative to the r direction, through what angle do I have to rotate to get to the f direction? If we call that angle theta, then for that angle theta, to get the perpendicular component of f, which is this or this, using this right triangle, I can see that that's equal to f times the sine of theta, right? The length of f, the magnitude of f, times the sine of theta would give me this side, which is f perpendicular. So I can replace f perpendicular with f times the sine of theta. So written in terms of that angle theta, and sometimes this is useful, the torque is the magnitude of that r vector times the magnitude of f times the sine of the angle between r and f. There's yet a third way to write it, which is sometimes more useful, and in fact I tend to use this one more often than the other two. And that is, if we extend the force vector direction backwards, so forward and backwards, make a line that includes the force vector, and then we define the perpendicular component of r to be the perpendicular distance from the axis of rotation to that line that contains the force vector. We'll call that r perpendicular, or sometimes we call it the moment arm for the force. What we do is extend the force forwards and backwards into a line and say, what's that shortest perpendicular distance to the axis? That thing is called r perpendicular. And notice that r perpendicular, if you label this angle here as theta, I probably should put it in there, then if I take the length of r, the hypotenuse, times the sine of theta, that gives me this side. So r times the sine of theta can be replaced by r perpendicular, or the moment arm. So a third way of writing it is the magnitude of f times the moment arm, which is just that shortest perpendicular distance from the f line, the line that contains f, to the axis. Three different ways of using it. Let's use that in an example, because the more you use it, the easier or more intuitive it will get to use it. Here I've got a pentagon-shaped object. I just did that because it was easy to do in PowerPoint. And it's pivoted to rotate around a fixed axis, which is shown here in the lower left corner. And I am applying a force along the upward direction of the screen of magnitude 5 newtons. And that point is a distance of 0.2 meters away from the rotation axis, and the angle of that displacement vector is 20 degrees above the horizontal. So there's just kind of some apparently random information, but useful information to that defines where and how strongly this force is being applied. And the question is, what torque are we applying to it? So I'm going to show how to do this with all three of these definitions. Using the first definition, what we could do is, the first definition says, take only the component of force which is perpendicular to that r vector direction, line that contains the r vector. And so to get that, what I would do is say, let's see, if this angle is 20 degrees, then this angle down here would be 20 degrees, and therefore this angle is 70 degrees. However you can figure out that, that's good. And so if I take 5 newtons times the sine of 70 degrees, that would give me this side, which is my f perpendicular. 5 times the sine of 70 is f perpendicular. And you multiply that by your r times f perpendicular. That's the first way. Second way, if I use rf sine theta, this defines that angle theta. In other words, if I go along the r direction, how much do I have to deviate to get to my f direction? That's 70 degrees. So magnitude of r times the magnitude of f times the sine of 70 degrees. Of course, that's the same as the first one. It has to be. And third, if I use the moment arm, r perpendicular, times the strength of the force, the moment arm is given by, if I draw the line that contains the force vector, what's this perpendicular distance over to that line? And so if I draw that right triangle in, that would be 0.2 meters times the sine, 0.2 meters times the cosine of 20 degrees. That would be that r perpendicular right there. 0.2 times the cosine of 20. So magnitude of f times r perpendicular. And the cosine of 20 is the same as sine of 70. So all three of these are exactly the same. Whichever one's easiest for you in a given particular situation, there's no right answer. Sometimes one of them will be easier than the other. None of them involved zero work in this case. Now, in doing that, I didn't really take into account whether it was a positive torque or a negative torque. If we, in order to assign a correct sign to the torque, we have to tell which rotation direction is positive. Just to be argumentative, here I'm taking clockwise to be the positive rotation direction. Notice that this force is tending to rotate it, or it's going to try to rotate it in the counterclockwise direction. So the force is tending to rotate it in the negative direction, and therefore the correct sign associated with all three of these should be negative. And sometimes it's just best to put in the sign after the fact to agree with your intuition. All right, let's try a voting question. We're trying to open a door that's stuck by pulling on the doorknob. Maybe it's jammed into the door frame or something like that, and there's too much friction, and we want to pull on the door. Here I'm saying door, it's drawn as a wrench, but we can imagine we're looking down from the sky and we're seeing the door from above. Pretend it's not it's a wrench, but it's a door. So we're saying compare this. We can either apply a certain force directly on the handle of the doorknob, or we can tie a rope to the doorknob and then pull on the end of the rope farther away from the doorknob. In which case am I exerting a greater torque? Or this one is phrased is, am I increasing the torque relative to the first case of the second case? Yes or no? Here the answer is no, and one way to see that is by doing the F times the moment arm. Remember, the moment arm is you draw the line that contains F and you multiply the magnitude of F times that perpendicular distance. And in this case, you'll see that the moment arm doesn't change by pulling in this direction. So if I draw the line that contains F, F hasn't changed and the moment arm hasn't changed, so the torque hasn't changed. And, of course, by pulling with a 5 Newton force here, that's the same as the rope pulling with a 5 Newton force there, so it shouldn't change. But the correct answer is it doesn't change. Second voting question. You're using a wrench to try to loosen a rusty nut. Which of the arrangements shown is most effective? And list them 1, 2, 3, and 4 in order of descending likelihood of effectiveness of each of the arrangements. So from most effective to least effective. All right, again, I can use the force times the moment arm to envision these. We're using the same force, so we just have to compare the moment arms. In this case, the moment arm is this big distance here, so that one's got a big moment arm. So situation 2 is the most likely. 1 and 4, as we discussed already in the previous one, have the same moment arm, so they're going to be equally effective. So 1 or 4 would be the next most likely. And then here, the moment arm is even less than the length of the wrench. If I draw the line that contains F there, that moment arm, that perpendicular distance, is even smaller than the length of the wrench. So it's going to be decreased even more. This one has a smaller moment arm, and therefore the torque is less. It will be less effective at loosening the bolt. Okay, so let's continue with the theme of wrench problems. I've got sort of a funky looking wrench here just to sort of beg the question of how to deal with torques and whatnot. We've got a strange bent wrench and we're trying to loosen a bolt. The bolt is located at coordinates in the xy plane 0.2 and 0.3 xy coordinates. And in the first case, A, we're pushing vertically on the edge of the wrench. And what magnitude torque are we applying to the bolt? That's the question. In the same configuration, instead of pushing upward right there, we're going to push inward with a different force. And suppose we want to ask, how hard do I have to push directly in on the arm of this wrench to the left to generate the same torque we got up here in A? And then C will make more sense when you look at it. It's got its own figure associated with it. So try parts A, B, and C, and we'll be back with the solutions.